Hi, I'm Eliran Rofe from IBM Research in Israel, and I would like to present a work I did with Samuel Ackerman, Eitan Farhi, and Orna Raz from IBM Research too. So let's start. The topic that I will talk about is detecting model drift using polynomial relations. This is the agenda. We'll start with the problem statements. What is the problem? What are our pain points? I will show our approach, how we want to solve it. I will demonstrate that our approach works as expected using several experiments. Then we will talk about potential extensions, or basically what we want to do right after the conference. You can also see our paper in archive. This is the link. So let's start with the problem statement. Let's say we have a data, we have trained a model, it works perfectly with 100% of accuracy, and we put it in production, everyone are satisfied, and 1 or 2 years later, something start to work not like we expected. And this makes a potential drift in the data. It may be, of course, other problems, but this is what the problem that we concentrate now. So what is basically the problem? The problem is that we have some initial assumption that both baseline data and field data come from the same distribution, even if it is an unknown distribution. But often this assumption is broken, and I will show an example, or a typical example in the next slide. And when we have this drift, we're likely to have an influence on the model performance. It means that the performance will decrease. So let's take a basic example. I am a cell phone model company, and I want to predict. I have a new cell phone model, and I want to say, to give it some price. So what can I do? I will take a model that I already have, which tries to predict the desired price of a new cell phone according to some features, technical aspects. So I have a data set of observations, which are past cell phone models. I have a list of features, which are technical aspects, physical measurements, and more. And let's say that I did it, I don't know, 10 or 15 years ago, before the smartphones era. We had, as you remember, for example, the battery life was very good. I had to charge my phone for, I don't know, 2 times a week. And now I need to charge it at least once every day. The screen size was very small, and now it is much bigger. We also have cases like keyboards that now no one has a real keyboard in his phone, right? It is not really important feature like it was probably 10 years ago that I had to click on the buttons. So there are many relations between these dataset features that are no longer exist. And this may give us a drift, right? And this drift may have a potential influence on the model, on the price prediction. And in this case, no one will be satisfied. Maybe me, because the price is too high or too low, and less people will try to buy my cell phone, or people that will see a price and say, oh, wow, it is too expensive. So what is our general approach? It is basically several steps. I have slides, and I will give more details about every step in a few minutes. The first step is identify polynomial relations between data features. I will show how, what is our self space, and more. After we have these polynomial relations, I will show how we measure the strength of each relation, because we want to work only with the strong relations. These relations can have some inherent relationship that we expect to have between the features. We'll calculate the amount of drift for every strong relation for baseline and field data. And then we'll do some comparison between the baseline and field with statistical approaches like likelihood function and Bayes factor. And this will help us to detect a change in the data distribution, and therefore to give an alert to the user that maybe the model is not good as it was before. Okay, so the first step is, as I said, is identify the polynomial relations. Let's start with a definition. We have a tabular structured data sets, right? We currently work only with structured data sets. We have n observations and m features. And we try to look for relations which are simple because I want it to be easy to compute. I don't want it will take, I don't know, weeks or months because it won't be really relevant anymore. I want it to be readable. So a client can look at a relation and understand what is the relation and what it means. It should also be robust because I don't want that small changes will have to do changes in my whole systems. It should also be relations that well represent the data. It means that they capture some significant traits of the data. Therefore, we decided on a search space, which is polynomial relations. We also defined two variables, which are k and l. K is the number of features which will participate in the relation. It is not including the target feature. The target feature is also a feature in the data set. We marked it as y, and k are two other features that will be source features for the relation. You will see it in the next slide. And also we define the degree L, which is the maximal degree of the polynomial relation that we will create. Now we'll define an embedding. For each target y, we define a potential relation. We also have a heuristic that we should do to decide which features will participate with the feature y. So in this case, we took a very straightforward, very easy heuristic, which is take y and find the two most correlated features. We mark them as x1 and x2. And now we have some embedding, which is basically all possible products of k features that are no more than L. The sum of them is no more than L. Here you can see that we have, when k and L are equal to 2, we have x1, x2, multiplicity of x1 and x2, square root of them, and also 1, which is x1 and x2 powered by 0, sorry. For these features and for the y feature, we'll define a temporary data set. Then we'll do a linear regression. We'll run the linear regression for over the temporary data set, and we can receive some function from this form that you will see here. What is this form? We have the features and we have coefficients, which are the coefficients of the linear regression. And now it is basically like a formula that its result or its prediction is y, right? It is the y value or the true value. Of course, it is related to how good we are or how good the linear regression was. And this is what brings us to the next slide, which is measurement. We need to measure if the formula that we saw in the previous slide is good enough, right? Because maybe the formula is very well captures the data, but maybe it is not. So we looked at several approaches of metrics. We selected the R squared value metric, but it is not that important. You can select whatever you want, whatever is good for you. And this metric means how far we are from the prediction. It means how far the true value is from the prediction that we had. If R squared is very close to 1, it means that we are very good and the relation is very strong. Everything is very accurate. If it is much lower than 1, it means that it is not good enough. Of course, in this case, we need to have some threshold and say, okay, if we are above this threshold, we define this relation as strong. If it is lower than the threshold, this relation is not that good. So now we have relations, and based on these relations, we want to detect a drift. We also have, if you remember, we also have strong relations. We don't use all relations. We selected a small set of them and consider them as potential relations for identifying drift. So the first term we should know is likelihood function. We have an input, which is the model parameters, theta. Basically, this is the regression coefficients, the beta values, and some variance. We also have our data input. It is a matrix X, which is the observations and features that you saw in the previous slides. And now we'll define the likelihood function as the product of the density function, and we evaluate it on every observation, on every X, small x. In in our case, this is a linear regression model, so the likelihood function is Gaussian, is normal. It also means that the prediction error is independent, it is normally distributed. What you should also know is that higher value means that we fit the Y value better. So this is probably what we would like to receive. Second term you should know is Bayesian information criterion, or BIC. Our input is now looks a little bit more familiar to what we saw in the first part of the slide. We have a linear model, the linear regression L1, and the data set D, which is basically the baseline data that we train the model on. And L1, as we remember, is learned from D. We did a temporary data set and all that. And now we can use this criterion to measure the fit on D. What we will do is take the BIC. It uses the likelihood function from the previous slide with some addition of penalties for using many parameters. We did the calculation, lower BIC value is better, but the more important thing is that we can take it and do some comparison between the baseline data and the field data. It means that after this comparison, we can know if the baseline and field data are more or less the same or have the same distribution. So for this case, we have the base factor. It is a comparison that's done by calculating the approximate formula that you see here in the screen. The formula is not that important. What's important to understand is the ranges. It means that we have three important ranges. The first one is when base factor is more or less equal to 1. L1 is fits to D and D tag, more or less the same, so it means that there is no drift. The second range, base factor is bigger than 1 or much bigger than 1. It means that the fit on D on the baseline data is better. And when base factor is lower than 1, the fit on D tag, the field data is much better. In our case, of course, it cannot be reasonable that the fit on D tag will be better because we learned L1 is learned based on D. But still, it is something that you should be aware of. Also for this, we have known thresholds that exist for this drift, and we can use this threshold to define if we are need to give some alarm to the user, okay, there is a drift, or we don't need to do it at all. We used several data sets. The first one was rain in Australia. Second one was London bike sharing, and third was a data set related to loans. All of them were structured data sets with many observations and numerical features. We didn't do any changes or something for them. These are the regular Kaggle datasets that you can find in the website. We did two types of experiments. This is more or less like a general design of these experiments. Later I will show you every specific details of every experiment. We try to simulate a change in the data distribution over time. It means that we took a data set, we split it randomly to two parts. One of them was considered as baseline data, the other was considered as field data. And we try to give some manipulation to the field data. So it will look like a drift that we try to simulate. We gradually increase this amount of drift, amount of manipulations. So we'll be able to see if there is some interesting mechanism in this case or how it is affected. Also, to make it more simple, L is equal to 2 and K is equal to 2. As you remember, the maximal number of features participate in the relation and the maximal degree. And what we want to see is that the base factor will grow much larger than 1 when the fit is not good anymore. It means that the drift, we had a lot of manipulations, and according to this, a lot of drift. So the first experiment is called raw permutations. Basically, if we represent our data set in an Excel sheet, like all observations are rows and all the features are columns, let's say we took every time a row, several values of the row and did some shuffling for them. it means that we inject some change, some drift to this field data, and we have a fixed percentage or a value which started of 0. P is equal to 0. It means there is no shuffle. You can see here in the right part of the screen that when P is equal to 0, the base factor is 1, sorry, for strong relations and weak relations. And when we increase the amount of shuffling, the amount of rows that we shuffle, you can see that for strong relation, it is significantly increased, but for weak relations, there is no change because the data is already pretty random. You can also see that when we do shuffling for something like 70% or 0.7 here in the graph, 70% of the rows, it is not increasing anymore. Why? Because the data is so random, so there is no importance almost for the base factor, because the data is really not, it is too bad anymore, it's too bad in this case. The second experiment we did is output variability. It is more like taking the data and add some synthetic Gaussian noise to the output. Also, in this case, we have a baseline data, which is D, a field data, which is D tag. We did the changes only to the Y tag, the output of the D tag. And in this case, when there is no variability, it means that the output was not changed. And also here, you can see that the base factor was very close to 1. But when we started to add some variability, how we called it, it is Y hat in this case, you can see that the strong relations had some significant increase in its base factor. This can be considered also like some fairness experiment. For example, if you will take the output and according to specific feature, you will decrease the values of the output values or something like that, but we called it variability because we don't have a specific direction. We didn't only decrease or increase the amount of values. It is just like a Gaussian noise. So here in this case, you can see again for strong relations that the base factor was rapidly increased, and for weak relation, there was almost no change. Lastly, the potential extensions. There are many extensions that we can do for this work. First one is more types. Now we support mainly numerical features. We can support categorical features too. This is done, for example, using logistic regression and not linear regression. It is a starting point. It's not everything, but it is a good start. This will lead us also to an option to do combinations of feature types, like numerical and categorical, and more other options. We also need to improve our feature selection heuristic. If you remember from the start of the slides, I said that we took the target feature and we have a heuristic which checks, which selects the 2 most correlated features to Y. This works well when the features are highly correlated to the target features, when X1 and X2 are highly correlated to Y. Also, for example, you can take a good relation, which is Y is equal to X1 plus X2, but maybe X1 and X2 are not correlated at all to Y, right? Because maybe they are well correlated together, but they are fully random to Y. So this makes us prone to errors. It means that we won't select, or probably won't select this relation. So this is not good enough yet. And this is something that we should improve. There is also a trade-off between the relation complexity, overfitting, readability, even performance. So it will make our code or our approach more robust. For example, I showed you that the degree is 2. I'm not sure this is the right degree. Maybe the right degree is 3. I don't know. But it is something that we should start to enhance the research in this area and to receive something more robust. Also, we considered every relation individually. It means that there is no dependency at all between relations. this is good in some points, but this can have some disadvantages. I also think that it is better if we be able to have some multiple hypotheses for the whole data sets, and then we can be able to give the user some number which says, okay, this is well likely to have a drift in your data set, but and not, it won't be based on some specific relations. But this, as I said, has advantages and disadvantages that should be considered. That's it, I think. Questions. I will be happy to hear questions and to answer questions.